So section 7.7 is called geometric sequences in series. So our goal is to be able to identify, write, and use geometric sequences in series. There is going to be some vocabulary mixed in throughout the notes, but just to give us a launching point, there's two definitions for us. A geometric sequence is a sequence with a constant ratio between two consecutive terms. That ratio is called the common ratio and is denoted by R. So here's your first example. We'll jump right into this. So example 1, so it has your term number n and your term a sub n. So n refers to your term number. The term is referred to by a sub n. So if, for example, this would be a sub 1 equals 4. This one would be a sub 2 equals 12, and so on. This sequence is a geometric sequence, and the reason being is if I want to go from 4 to 12, I multiply by 3. If I want to go from 12 to 36, again, I multiply by 3. If I want to go to 36 to 108, multiply by 3. From 108 to 324, multiply by 3. So this is what's meant by a constant ratio. It's the same between each term. So the sequence is a geometric sequence since for n equal to 1, so for our first term, a sub 1 is 4. We identified that right here. And your R, your constant rate, is 3. So for each time you're multiplying by 3. And you have that a sub 2 equals a sub 1 times 3. So 4 times 3 is 12. A sub 3 is a sub 2 times 3, or 12 times 3, which is 36. And if we wanted to continue this on, we could, but there's a shorthand notation we could use. We could say a sub n equals a sub n minus 1 times 3. So if I want to know the value of my current term, I'll use the value of my previous term and multiply it by 3. That's all this formula says down there. So a recursive definition for the sequence is a sub n equals 4 if n equals 1, and 3 times n minus 1 if n is bigger than 1. So how do they come up with that definition? There's an easy way to do this. Write a recursive definition for a geometric series, and that's using this form. So the general recursive definition for a geometric series is given by a sub n equals a sub n for n equals 1, and a sub n minus 1 times r for n bigger than 1, where a sub n is your first term, and n is the term number, and r is your common ratio. So keep that handy as we look at the next example. It says, is the sequence geometric? If so, write a recursive, oops, sorry, you can't see it. It says, is the sequence 12, 9.6, 7.68, and 6.144 a geometric sequence? If so, write the recursive definition for the sequence. So to get from 12 to 9.6, what do I need to multiply by? And an easy way to come up with that number is just to get your calculator and do 9.6 divided by 12. Because if it's geometric, then I should be able to do 9.6 divided by 12, and that would give me my ratio. So in this case, it's 0.8. So this would be 0.8. Check and see if, now you can just check and see, is 9.6 times 0.8 equal to 7.68? So if we do that, we do get 7.68. So this would be times 0.8. And then let's do 7.68 times 0.8. And you get 6.144. So times 0.8. So this is true. The first one we divided. So 9.6 divided by 12 get us 0.8. So if I did 12 times 0.8, I would get 9.6. So this is geometric. Since it is, we're going to be able to write a recursive definition. So what we need to identify to write our recursive definition is we need to identify what A sub 1 is, and we need to identify what R is. So A sub 1 is your first term. Our first term here is the very first number, which is 12. Our rate, what are we multiplying by each time, is 0.8. So our recursive definition then is going to be A sub n equals, and like a little brace, A sub n for n equals 1. So for us, our first term is 12 when n equals 1. And then A sub n minus 1 times your rate, which is, in this case, 0.8, for n is bigger than 1. So pretty straightforward. That's your recursive definition. A recursive definition allows you to find any term in the sequence without knowing the previous term. Actually, that's a typo. That should say an explicit definition. An explicit definition allows you to find any term in the sequence without knowing the previous term. So translating between recursive and explicit definitions. The general explicit definition for any geometric series is given by A sub n equals A sub 1 times r to the n minus 1 power. So example 3a, given the recursive definition A sub n equals 12 if n equals 1 and 1/3 A sub n minus 1 if n is bigger than 1, what is the explicit definition for the sequence, and then use it to determine the value of the 10th term of the sequence. So the first term, that's when n equals 1, so that would be 12. The common ratio, that's the number in front of your A sub n minus 1, which is, so this would be 1/3. The explicit definition, so this is where we're going to use this translation up here. So it's going to be A sub n equals A sub 1 times r to the n minus 1. So this would be A sub 1 equals A sub 1, so this is 12, your first term. We could write that A sub 1 is 12. So A sub n equals 12. Your rate, so we'll put parentheses, or your common ratio rather, is 1/3 time to the n minus 1 power. So finding the 10th term of the sequence amounts to doing A sub 10 equals 12 times 1/3 to the 10 minus 1 power. So this is 12 times 1/3 to the 9th power, which if you put in your calculator, you would get about 0.0006. Example 3b, on the next page, says, given the explicit definition A sub n equals 6 times 1.2 to the n minus 1, determine 23rd term of the sequence, and then what's the recursive definition? So they just want us to find the 23rd term. So that amounts to saying A sub 23 equals 6 times 1.2 to the 23rd power minus 1, which is 6 times 1.2 to the 22. So, and if you plug that into calculator, you would get about 331.24. Identify the first term. I mean, this is really similar to when we studied exponential functions, and we said this is the value out front's your initial value. So your first term is similar to your initial value. So this is going to be A sub 1 equals 6. Your common ratio, that's the value in your parentheses, similar to your growth factor. Your common ratio here is 1.2. So your recursive definition then is a sub n equals, put a bracket, your first term is 6, so that's 6 when n equals 1, and then your common ratio is 1.2 times a sub n minus 1 if n is bigger than 1. So that's your recursive definition for example in part B. Example 4 says a phone tree is when one person calls a certain number of people, then those people call the same number of people, and so on and so forth. In the 5th round of class, 243 people were called. The first person calls 3 people. So what's the first term? So our a sub 1 in this case is 3 because the first person calls 3 people. We're also given the 5th term because it says in the 5th round 243 people were called. So we're also given a sub 5. This is 243. Use the explicit definition to find your common ratio, R. So the explicit definition, which from the last slide is a sub n equals a sub 1 times r to the n minus 1. For a sub n, we're going to use a sub 5 because we're given a sub 5. For a sub 1, we're just going to use a sub 1. For r, we don't know r, that's what we're trying to find. And n, we're going to use the same n we used for a sub n, so we'll use 5. So now I'm going to simplify this. I know what a sub 5 is. A sub 5 is 243. I know what a sub 1 is. It's 3. I don't know what r is, and I could do 5 minus 1 and get 4. So we solve this for r. So divide everything by 3. So this would be 81 equals r to the 4th. If we can get fancy, we could say the 4th root of both. Take the 4th root of both sides, and you'd get 3 equals r. So your constant ratio is 3 in this problem. So to write your explicit formula, remember the explicit formula is a sub n equals a sub 1 times r to the n minus 1. So your explicit formula is a sub n equals a sub 1, but we identified a sub 1, it's 3. So this is 3. Your constant ratio, we just found that is 3 as well. And then n minus 1 power. In part E, how many people were called in the 8th round? So we're going to do a sub 8. So this is going to be 3 times 3 to the 8 minus 1, which is just 3 times 3 to the 7. Oops. And you could plug that in your calculator and you would get 6561. So 6,561 people were called in the 8th round.